Hello and welcome to Phased Array Tutorials. This is tutorial 3 on using S parameter file for digital phase shifter and digital attenuator for an accurate phase array system design. Pretty interesting topic. Here is the agenda which we will cover in this video. Lot of interesting content. So I hope you will watch the video till the end and take all the benefits out of it and apply in your own phased array system design. Now, before we start, subscribe to my channel, click on the bell icon to enable all the notification and give it a thumbs up and share it with your friends and colleagues who may be interested in watching similar tutorial. All right, let's go ahead and understand each of these topics in more detail and enhance our knowledge. Now here I'm taking the example which I discussed in tutorial number 1, which is a pretty straightforward 16 cross 16 phased array system design. And you can see I have set the variables here of 16 and 16, working at the frequency of 10 gigahertz with theta and phi defined as variables at 0 degrees. Now, once we go ahead and perform this phased array system, we can look at the plots in terms of the 3D beam, 2D cross-section phi cut, and also the UV plot. Now, after our simulation is complete, we have this data set, and once you open that data set, you can see variety of category where you can look at different array measurements or the beam related measurements and so on. Here, I'm going to talk about a specific category here called part info. Now in that part info, you can notice the X and Y location of the array depending upon what you have provided in this array antenna component. But more importantly, you have a part info on attenuation and part info on phase shifter. So currently with my setup, if you look at array attenuation, it's -1 dB in all 256 channel because we are working on 16 cross 16 system. And also, if you look at the phase shifter, you can see the phase is determined to be 0 degrees because obviously we have theta and phi defined as 0, beam looking upwards. So no surprise here. Now in phase shifter, when we steer the beam, this theta and phi are being inputted as the variable. And now phase shifter component calculates, and the mode is set to auto. It will calculate the phase shift required in different channels based on where we want to steer the beam. Also in attenuator, if we have to reduce the slide lobe level, we can apply a specific window, and that window will determine what should be the amplitude in different channels. So currently you can see there is no windowing function applied, hence all the path is seeing -1 dB. Now to enable the windowing, we can double click on that component. Instead of none window, we can select the type of window we would like to use. So in this case, I will go ahead and use a Taylor window with the desired side lobe level of -20 dB. And the insertion loss again is defined as 1 dB. Now once we apply this window and keep track of what happens in the loss or the amplitude requirement in all the channels. So before we go ahead, this is our standard beam where you can see the peak is around 24 dBi and the first side load level is around 9.3 or 10 dBi, which is close to 13 dB side lobe level, which is what we would expect. Now we will go ahead and checkpoint this graph using this icon here or pressing C. And now we already changed the window to Taylor. We can go ahead and apply a simulation and look at the comparison of this plot. And here now you can see this solid line. The side lobe level is approximately 2.3 dB, where the peak is around 23.6. So it's better than 20 dB, and that's what we wanted this window to achieve. Now, if we now look at the array attenuation amplitudes in different channel because of windowing, you can see the amplitudes are now different in each channel depending upon the profile. You can also see this data by simply right-clicking and adding this data to a graph. And here you can see attenuation on each channel. Don't worry about this x-axis. You can always set it to the increment of 1 or whatever required. You can read the attenuation in each of these channels. Now, once this is done, we know, what we have to, expect in terms of from the digital attenuator from whichever company we might be buying it from. Now, let's talk about phase shifter. Now, phase shifter, if we steer the beam, let's say 2020, and before I start simulation, let's go to phase shifter. Now you can see originally when your beam is zenith looking is all 0 degrees, right? Now I change these variable to 2020. These variables get passed on to this component. Calculation mode is auto. So wow, when we run the simulation, the component will calculate the phase shift required in different channels. And now you can see after the simulation is finished, the phase shift requirement in each channel if we have to steer the beam at a certain theta and phi. And you can keep playing on it. This phase shift requirement will keep on changing. And in our 2D plot now we can see the beam has shifted to 2020 degree, and now we can go ahead and clear the checkpoint to get rid of the older result. And now we will keep this result as our checkpoint, because now while we have applied the phase shift and the Taylor window, these components are still ideal components, right? There's no restriction on how much precision you might need and whether the real world component can actually give you that precision or not. So now we are slowly going to introduce the real world phenomena in these components so that we can see a little more practical phased array system response. So the first thing I would like to do in array attenuation, you can see quantization is set to no. By making it yes, you can either do it in terms of number of bits, which is like uniform. Most of the off the shelf phase shifters will or attenuators will work in that format. Or if you have designed your own custom array attenuator, you can define custom level. For this tutorial, I will just use number of bits, and depending upon whether you are using a 5-bit attenuator or 6-bit attenuator, you can enter number of bits. For this tutorial, I will just use number of bits as 5, and the step size to increment the phase, the attenuation is 0.5 dB. Pretty practical, a specification which you can get from component. So I applied quantization in my phased in my attenuator. Now same thing I would do in phase shifter, and we go to quantization, number of bits, and in this case I'm going to use number of bits as 4. Now, when we do that, remember the insertion loss in the phase shifter is 1 dB. Insertion loss in the array attenuator is 1 dB. That means whatever number you are reading in the array attenuation, the actual attenuation required in the channel is less than what you are seeing here, because this includes 1 dB of insertion loss. So the raw attenuation required from attenuator is 11.2 dB at this point. But now, after we apply the quantization, when we run simulation, you will not see these kind of decimal digits, because now the results will be truncated to the step size which you have just entered. Now you can see in all the channels you are seeing 0.5 dB increment base data. Now if you compare the response, there is no major love lost between the ideal attenuator or with quantization. You are still able to achieve what you wanted. Also, the beam direction is still at 20 degrees, and you can steer this beam in all desired requirement to make sure your 4-bit phase shifter is able to steer the beam with the precision which you are really looking at. All right, so this was all about quantization. How do you see the results? And here in phase shifter, again, you can see, because I use 4-bit phase shifter, the phase shift among different branches is now restricted to 22.5 degree increment, as you would expect. All right, so now the last thing we need to think about, that I may not design these components. These components I might be buying from certain vendor. So how can I bring the real world vendors, measurement data into my system design so that I can get an accurate representation or what's going to happen, how the real world part imperfections, because the amplitude, the attenuator will have, amplitude settability error. If you needed 0.5 dB, it may not be exactly 0.5 dB into your frequency. And at the same time, any practical part will also introduce a phase shift, which is currently not modeled in your system. While you are taking care of one practical stuff, which is about quantization, that means fixed number of bits, but you still don't know what will be the phase shift introduced in different path. Similarly, the phase shifter component will have phase settability error. That means if you need 22.5 degree, you may not get exactly 22.5 degree, right? You will have certain plus and minus tolerance associated. Also, each phase shifter will have its own insertion loss, and that insertion loss will vary based on the frequency and the state you are referring to. It's not going to be uniform. So all those system, practical, aspects have to be accounted for when you do this kind of system design. Otherwise, your simulation tool is of no use if it can't do the practical modeling to allow you to do an accurate system analysis. There's no point using that tool. You can very well do pen and paper calculation and you still be able to make your systems. All right, so let's see how practical simulation the system view software will allow me to do. Now for attenuation, I will go ahead and set this parameter called use as parameter, which is currently set to no. And notice the insertion loss is 1 dB. When I switch it to yes, now it knows you are going to use an S parameter. So there is no point you defining the insertion loss, because that data is already there in the S parameter file which you are going to use. Then you have two options here, dataset and file. If you want to keep all the S parameter file for individual state, and for 5-bit phase shifter, I will have 2 raised to 5 states. That's 32 S parameter files. So all those files will have all the phase information, attenuation, insertion loss information. So you can keep those files somewhere in your hard disk. And the simple thing you need to do is browse to the first file which has an index 0. And I will shortly talk about this indexing and how should you go about this indexing. The first file, which is referring to the least attenuation, which is typically 0 dB. When I say 0 dB, only the insertion loss will be there. There is no additional attenuation introduced by that component. So you refer to that first file and that's it. The second option is I can read those files and have a data set inside my workspace. And this is what I have done. And then you refer it to appropriate data set. Again, the same concept, the index will be there. And this name will be automatically generated based on the S parameter file, which you have obtained from the vendor. So once you do this, now how do I import these S parameter files into system view? Well, it's very simple. The workspace you are working on, I simply right click, add a folder. And here under SNP folder, you can see I created an attenuator folder where I do have 32 S parameter file in a specific indexing format. Now to import bulk S parameter files into system view, it's very straightforward. At any folder, you right click, import, and as data file, and you can browse to the directory wherever you have kept as parameter file, select all of them, and with one click you will have all the parameter files imported. And this icon represents dataset, this green line icon. So that means you can open this file now. It is just like any other dataset. You can see S11, S21, S12, S22, and so on and so forth. So all the data are visible. So I have 32 S parameter file because remember I'm using a 5-bit attenuator. And then in a phase shifter, I have 4-bit phase shifter. So I have 16 S parameter files of the phase shifter. So now let's also go to phase shifter component, set use S parameter file to yes, and browse to the first file, which is 0 degree phase shifter file. Click OK. And now we are ready to run simulation. And once we run simulation, let's see the performance criteria. So let me adjust this size a little bit, and let's go ahead and run simulation. Now, all the simulation is happening with the practical S parameter file. And now you can see the difference. The dotted line is your idealistic component. The solid line is with your practical S parameter file, while the main lobe and the first side lobe isn't necessarily deteriorated, but you can see there is a significant change in the second side lobe and so on. So those are practical imperfections caused by the real world component. Now I spent some learning here, so let me close this option here for the moment, and let's extend this data set little down. Now, when we use this as parameter file into our design, you see this exclamation mark becomes yellow, indicating there are warnings. If I click here, it is telling you that you are using S parameter in these kind of components. They might result in different impedances across different paths. And obviously that will happen because S11 of every state of either phase shifter or an attenuator will be different. So it is telling you the one path approximation which is being used in your current analysis may not give you accurate impedance values across all the paths. And that's the default setting in your phased array controller. And you can also see the yellow exclamation mark here. So enough pointers for designer to know there is some warning somewhere. So if I double click on this phased array controller, if we go to options, you can see the system impedance computation is happening with one path approximation, which is absolutely fine if you're using an ideal component which has no dependency on the frequency domain data. But right now that's not the case because I'm using an S parameter file. Each channel may have different S parameter file, hence the different impedance. So instead of using one path approximation, I can switch to full system solver. Now system simulation will take slightly more time, but it will be more accurate. So let's go ahead and run this analysis. And now once the simulation finishes, you will notice this exclamation mark will stay white. Although currently in terms of beam performance requirement, there is no major change. But again, you can't leave those things for chances. Now let's talk about the attenuation. So if you look at part info, attenuation of the attenuator, you can notice the required attenuation. Now this one is using minus 13.5. Our earlier simulation was using minus 12 dB, out of which 1 dB was the insertion loss. So the actual attenuation required was 11 dB. But here it is using 13 dB. So what's going on, right? There is some issue. But before we get and resolve that issue, look at attenuation. Here you also have the phase. So it is reading the phase at 10 gigahertz from all the required S parameter files. And obviously you can see the phases are different because you're using different attenuation value. And if you're using different attenuation value means you're using different S parameter file. So pretty much logical. Now, similarly, if you go to phase shifter, the phase shifter has its own performance among different, kind of branches. Now, how do we know which of these files are, getting used by the simulator? That information is shown to you under part info state. If we go to part info state and look at attenuator, you can see the index number of the files which have been used in different path. The first path obviously is 22 index. So if we open the attenuator and look at the 22nd index, which is basically this file here, with the file name, I know it's 11 dB. And that's the advantage if you put some information here so that you can quickly recognize what is the value of attenuation or then ideal expected attenuation. So file number 22, if we double click on that file and open it here, and look at the data which is near 10 gigahertz. So the nearest point I can find is 10.01 gigahertz. And if you look at S21 is around minus 13.59. And what is being used here is basically 13.587 because that's the interpolated value between these two frequency points, because exact 10 gigahertz is not available. So you see how beautifully tool goes and picks up the data from the S parameter file without user having to worry. And it also tells you which state exactly I'm using, so that in case you need to cross check or you need to do some fine tuning or array calibration, you can always go ahead and do that. Similarly, in the phase shifter, it is telling you the file index, which is using to introduce the desired amount of phase shift required to steer the beam at that direction. Now, lastly, how do you know which file is getting picked up? Is there a rule? How will tool know which attenuation value or which phase shifter value it should go to which file and all that? The simple rule to remember is doing the proper nomenclature of these files. The file name can be anything. No matter what you do, doesn't matter. The first dot where the tool will look for, you should always have an index before the first dot. So here you can see there's underscore 0, underscore 1, 2, 3, 4, 5, 6, 7, 8, 9, and then you have 10, 11, 12, and so on. And you will have the last index, which is 31 here. So 32 is parameter file. Similarly, in the phase shifter, doesn't matter what you specify here, but the index again will be from 0 to. So the simple rule, no matter which S parameter files you are bringing in, you just put the proper index. Now, what you put between the first dot or second dot is optional. If you want, you can just say, no, the file name underscore 0.s2p. But you can put some additional detail here. As you can see, point, dot, and then I, entered as 0 dB, 1.5 dB, 0.5 dB, and so on and so forth. 0.5 dB, 1 dB, and so on. So this information will make your job easier. When you look at the index number here, you can quickly see which corresponding value that file might be referring to, and so on and so forth. Simple rule to remember. All this is very well documented in system view. So in case you get into some confusion, refer to the documentation, you will get your answer. So you saw in matter of few minutes, you would be able to perform a very accurate system analysis using the real world component. And not only that, take all those imperfections in your real world components, whether it is amplitude settability error, phase settability error, insertion loss, information, all that can be accounted by this nice system simulator tool, so that you can have much more confidence in the result which you are obtaining from your system design. So that's all for this video. I sincerely hope you enjoyed the content presented in this video, and it will be helpful for you when you talk about your own system application or system design. Thanks a lot for watching. Stay tuned for more videos in this series and wish you all the best with your design work.